Welcome back. In the last lecture, I introduced the concept of Brownian motion. It is basically a continuous time, continuous variable random walk, and I also started discussing the calculus of functions of Brownian motion. We were in the process of arguing that the conventional Newtonian calculus does not constitute the appropriate framework for the differentiation and integration of functions of Brownian motion. We introduced the example, a very simple example, that in Newtonian calculus we have the d of x square is equal to 2x dx, and if we apply the same logic to Brownian motion, we must have d of w s w t square should be equal to 2 w t d w t. We continue with this, we integrate both the sides of this expression between any arbitrary limits 0 to t, and then we started evaluating the two sides. We started with the evaluation of the right hand side, and we found that the expected value of the right hand side turns out to be 0, and we arrived at another result. The other result that we arrived at is this one, that d of integral of the squared of Brownian motion is equal to t. These were the two results that we arrived at in the last discussion. Now, if Newtonian calculus was to hold, then because d of x square is equal to 2 x dx, and if we integrate both sides and then we take the expectation values, they should be equal. The expectation of the right hand side we have found, the expectation value of the right hand side we have found to be 0. Therefore, if Newtonian calculus was to hold, the expectation of the left hand side should also be 0. That means, this expectation should be 0, but it is quite obvious that the expectation of this expression is not 0. For instance, let us work out this d of w s squared, and this turns out to be, if you integrate between 0 and t, this turns out to be e of w t square minus w 0 square, which is not 0, and in fact, we shall arrive at the reason for this, but for the moment this is not 0, and therefore, it is clear that the expectation value of the left hand side and that of the right hand side do not coincide, and because the expectation values do not coincide, there must be some difference in the integration, because if the integration results were the same, the expectation value of the integration results should have been the same. Putting it the other way around, because the expectation values are different, there must be some difference in the integration. Now, we start about, or we explore the reasons, the cause of this anomaly that arises in the case of Brownian motion. Now, when we talk about Newtonian calculus, as you can see here, we start if we do a Taylor expansion. If we do a Taylor expansion of x square, what do we get? We get d of x square is equal to 2 x dx plus f double dash x, that will be 1. So, 1 by 2 into 2 into dx whole square. If you I can also write it now explicitly, f dash x is equal to 2 x. So, the first term is 2 x into dx, and f double dash x is equal to 2. So, 2 into 1 by 2 will give me 1, and then we have dx square. But as you saw in the beginning of today's discussion, we assumed that d of x square is equal to 2 x dx. In other words, what we are trying to portray, or what we are trying to what is the implied assumption that we make while doing Newtonian calculus, that higher orders of dx are so small enough that we can ignore them. In other words, dx itself is small, so small that we need to retain only first order terms in dx, and higher order terms in dx, that is dx square and above, can be neglected, and therefore, d of x square we can take it as 2x dx. The dx term is small enough for to justify this approximation. However, when we move from the Newtonian framework, which applies to deterministic functions, to the stochastic domain, to the functions of Brownian motion, we have a slightly different situation. Let us do the same Taylor expansion for d of w t square. W t square is square of Brownian motion. We do it Taylor expansion of d of w t square. What do we get? We get 2 w t, in analogy with this expression, we get 2 w t d w t plus d w t whole squared. As far as this expression is concerned, we have no problem. This is absolutely similar to what we have here in the conventional framework. So, they are analogous. The problem arises when we talk about d of w t squared. In this case, dx squared was small enough to be ignored, but that does not happen to be the case when we talk about d w t squared. D w t squared, as will be shown later when we transform it using a normal variate. In fact, we have already done it. D w t square has integral of d w t square has a value of t. Therefore, d w t square has a value of d t. I shall be talking more about its mean and variance, so that it becomes clear that this is non-stochastic in a few minutes. But for the moment, d w t square is of the first order in d t. That is the most important thing, and because it is of the first order in d t, it cannot be ignored. So, the second derivative, or the term arising from the second derivative of the function in the Taylor series, cannot be ignored, in contradistinction to the term that arises in conventional calculus, where we ignore the second derivative term, because that contains dx square and dx is small enough for dx square to be ignored, but dw is not small enough for dw square to be ignored. That is the important thing. We shall come back to it again in a minute. Let us further explore it geometrically. Now, when we try to work out the length of an arc, we have a given function y is equal to f x. We try to work out the length of an arc between any 2 points x equal to a and x equal to b. How do we do it? We integrate ds between the limits x equal to a and x equal to b. What is ds? ds is an infinitesimal length, say for example p q. We take this length p q and we integrate it over the entire length. Then what do? We write this p q infinitesimal length in terms of dx and dy as dx square plus dy square square root. Now, the very fact that we are writing ds as under root dx square and dy square conveys a very important geometrical meaning. The geometrical meaning is that we are assuming that in this region C D, which is of length dx, the curve is a straight line. The region ds, or the interval dx is so small that in this small infinitesimal interval, the curve can be approximated by a straight line, and therefore, we can apply the Pythagoras theorem and write ds as under root dx square plus dy square. Of course, then we simplify it and we write it as dx under root 1 plus dy upon dx whole square. Now, this is also equivalent to this summation of series. As you can see, summation up to n, and then take the limit n tending to infinity of 1 plus dyi. But the important message at this point of time is that the points p and q on the curve y is equal to f x. This is p, this is q, this is p, this is q. The points p and q on the curve y is equal to x are assumed so close to each other that p q approximates a straight line, and therefore, we can write the distance p q as sum of square root of dx square plus dx y square using the Pythagoras theorem. So, what is the fallout? The fallout is that at the infinitesimal level, when we talk about Newtonian calculus, when we talk about conventional calculus, we assume that the entire curve is constituted of infinitesimal straight lines combined together in an appropriate pattern. At the infinitesimal level, if I were to zoom in very high, I would see only a straight line. That is the important thing which is conveyed by the Newtonian calculus, which is violated in the calculus of Brownian motion, calculus of stochastic variables. Another example relates to the area. In the case of area also, what do? We integrate y dx, and when we integrate y dx, you can clearly see that y is this length. This is the initial value of the function, and then we multiply it by dx. In other words, what do we assume? We assume that this particular y into dx is a rectangle. In other words, we assume that the PQ length is a straight line, is approximating a straight line in this small domain dx, and as a result of it, the strip is nothing but a rectangle, and because the strip is a rectangle, the area of the strip is given by the initial value and the forward increment. The forward increment is dx. So, this is y into dx, which is given here. So, that is another example of where conventional calculus assumes that at the very small level, at the infinitesimal level, deterministic curves are constituted of small assortment of straight lines, or assortment of small straight lines. But that does not happen in the case of Brownian motion. Let us see why. Now, as far as conventional calculus is concerned, as I have just mentioned, what we do is we truncate the Taylor series if we assume that the point at which the function is to be evaluated, that is x plus dx, is so close to x. In other words, dx is so small. Dx is so small that higher powers of dx, higher order of dx are redundant, and therefore, we truncate the series at this point, and we get dy is equal to dfx f dash x into dx. This is what we did in our example also. F dash x was 2x. So, 2x into dx was what we got of d of x square. Dy is equal to f dash x into dx, and that is the end. We do not consider higher power terms why dx is so small. But when we talk about Brownian motion, let us proceed. Let us continue with the series. The first term poses no problem. It is analogous to what we have in conventional calculus. So, this is correct. The issue is about the second term, and the issue is not only about the second term. The issue is about this expression dwt or dwt squared. Let us look at this carefully. As I mentioned when I enlisted the properties of Brownian motion, that dwt can be written as z d t under root, where what is z? Z is standard normal variable. So, what do we have? dwt into dwt gives us z square dt. So, this expression dwt is nothing but z square dt. So, what is the expected value of dwt? It is quite straightforward. The expected value of z square is 1. So, the expected value of this expression is dt. So, expected value of this expression is dt, because expected value of z square is 1. So, that being the case, the first thing we get is that this expression is, at least in the mean, at least in expectation, is a first order term in dt, and because it is a first order term in dt, at least in expectation, you cannot ignore it. You cannot ignore it like you did in the conventional calculus. You threw away dx square, but you cannot throw away dw square. Why? Because dw square is equal to dt, at least for the moment, at least in expectation, and therefore, it is to that extent it is relevant in the Taylor series, it cannot be excluded from the Taylor series, and that is one thing. Let us look at the variance. When we look at the variance of dWt, what will it be? It will be the variance of z square into dt square. See, if the dWt is given by this, so dWt square is given by z square dt. Therefore, the variance of dWt square will be given by the variance of z square into dt square. What is the variance of z square? The variance of z square is 2, which we shall establish very soon, but the variance of z square for the moment, just take it from me, that it is equal to 2, and therefore, the variance of dWt is 2 dt squared. Now, dt squared is very interesting. The variance of a stochastic process is of the order of dt, is in first order in dt. Brownian motion is a typical example. Brownian motion has a variance which is of order dt. Scaled Brownian motion also has variance of order dt. However, in this case, in this particular case, we are finding that the variance is second order in dt. What does it mean? If dt is small, that means the variance is very, very small. And if the variance is very, very small, what can we say about the variable? dWt or dWt square. If the variance is very small, we can approximate it by a non-stochastic variable, because variance is very small. Variance is of the order dt squared, and normal stochastic processes have a variance which is proportional to dt. So, because the variance here is smaller than what is smaller in order compared to the variance of normal stochastic processes, we find that dWt not only has the mean dt, but is also got a very, very thin variance, and therefore, is almost deterministic, and as a result of which it is equal to dt not only in expectation, but is also throughout at a deterministic level equal to dt, and therefore, obviously it cannot be ignored. So, you can write this expression as f dash Wt dWt plus 1 by 2 f double dash Wt, and this expression can be replaced by dt. So, that is the reason why conventional calculus breaks down when we talk about stochastic variables, because the second second increment, or the square of the increment, which we ignore in conventional calculus, becomes a finite deterministic value, at least at the first order in the case of stochastic calculus. And because it is of the first order in dt, you have to take it into account in working out the differential. Right, we had used two results here. E of z square is equal to 1, variance of z square is equal to 2. Quickly let us work them out. Now, E of z square is equal to 1 is quite straightforward. E of z square is equal to 1 arises from this E of z, or let me put it, variance of z is equal to what? Is equal to E of z square minus E of z whole squared. Now, this is equal to 0, this is equal to 1. So, this must be equal to 1. So, this is elementary. The second part is slightly more interesting. For that, we work out the expected value of z to the power 4. So, when you work out z to the power 4, you find that putting the value of the normal PDF, we have z to the power 4 e to the power minus 1 by the standard normal PDF. We have 1 upon root pi. This is the standard normal PDF, 1 upon root pi e to the power minus 1 by 2 z square dz. So, this is the standard normal, multiplied by z4, you get E of z4. The integral is an even function, as you can see straight away. So, the limits from minus infinity to infinity can be written as 0 to infinity, and you multiply by 2, because the integral between infinity and 0 is the same as the integral between 0 and minus infinity. So, you take the integral 0 to infinity multiplied by 2. Make this substitution here, and after you make this substitution, you arrive at this expression. and this expression, if you look carefully, is nothing but the gamma function with the argument of 5 by 2. If it is t to the power 3 by 2, it becomes the argument of the gamma function becomes 5 by 2. We simplify this gamma 5 by 2 using this iterative relation gamma n plus 1 is equal to n gamma n. We use this expression and we end up with gamma 1 by 2. Of course, these two terms come into play because using this n quantity, gamma 5 by 2 is equal to 3 by 2, gamma 3 by 2, that is equal to 3 by 2 into 1 by 2 gamma 1 by 2, that is precisely what is done, 3 by 2 into 1 by 2 gamma 1 by 2. Gamma 1 by 2 is equal to root pi. You substitute these values, you find that E of z square is equal to 3, and therefore, variance of z square is equal to E of z4 minus E of z4 is equal to 3, I am sorry. Therefore, variance of z square is equal to E of z4 minus E z square whole square, and this expression is 1, we have shown already. This expression is 3, we get from there. So, this is equal to 2. This is the proof of gamma 1 by 2 equal to root pi, and this is quite straightforward. Instead of the conventional method of integration, I have used the property of the standard normal variate, that integral minus infinity to infinity 1 upon under root 2 pi e to the power minus 1 by 2 z square has dz must be equal to 1, because it is the integration of the PDF over the entire range of entire spectrum of values of the variable, and therefore, it must be equal to 1. This is what I have used here to simplify this expression. I have used it here and I end up with root pi as the answer. Now, so far we have discussed the problems, the issues arising from the use of Brownian motion as model for modeling of stochastic processes. In other words, we have discussed how the conventional framework fails when we talk about stochastic calculus, when we talk about calculus of functions of stochastic variables. Now, let us see how do we do it. We have discussed the problems, but what is the solution? Let us now look at the solution. The solution is provided by a very celebrated lemma, which carries the name of the person who has propounded it, and that is Ito. Ito's lemma. It's it forms the cornerstone in a sense of stochastic calculus. So, Ito's lemma says, if g x t is a continuous and at least twice differentiable function of a stochastic variable x and time t, and x is the stochastic variable which is defined by this expression, x is defined by this stochastic differential equation, and g is a function of x and maybe an explicit function of t as well, then this holds. The total derivative of g is given by this entire expression. That is what we have to establish, right. So, we start with a function g x t and we do a Taylor expansion. When we do a Taylor expansion of for g with respect to x and t both, what do we get? We get dg is equal to partial of g with respect to x dx, partial of g with respect to t 1 by 2, second partial of g with respect to x dx square, second partial of g with respect to dx dt, dx in dt, second partial with respect to t 1 by 2 of course dt square, and so on. Now, this term is straightforward, it is linear in dx, so we have no problem with it. This term is linear in dt, so we have no problem with it. Our problem starts arising from the third term onwards. Let us explore the three terms which are of second order derivatives. Let us start with dx square. Let us start with exploring this term. Dx square, let us see what it gives us. Dx square is equal to, by definition, dx is equal to a dx plus b dw. Therefore, dx square is simply the square of this. Now, when we do the squaring, we get one term dt square, which is second order in dt, so we throw it out. We get one term in dw square. We have just established that dw square becomes deterministic in t it becomes dt, it is deterministic in dt. So, dw square will be replaced by dt, because it is deterministic in dt. You can put dw equal to z d under root dt and then square it, and you will get that. So, this term remains, it becomes b square dt, b square, z square has the expectation value. So, in expectation it becomes b square dt, right. So, the expectation of this term, the expectation of the square of this term becomes b square dt, because the expectation of z square is 1. What about the term dt dw? That is of the order dt under root dt, that is dt to the power 3 by 2, which is again greater than dt. So, we again throw it out. So, in other words, when I expand this dx square, the only term of relevance and the one term of relevance, it is not only the only term, it is also the one term of relevance, which is b square dt, which is the second term. Now let us look at the other what you call increments. Dx into dt, dx into dt will involve dt into dt, that is dt square. So, that is to be thrown out. dw into dt, we have shown that this would be of the order of dt to the power 3 by 2. So, this also goes away. dt square is of the second order in dt. So, this also goes away. In other words, out of this entire set of second order derivatives, the only thing that remains is 1 by 2 d square g upon dx square into b square dt. That is the only term that remains out of this entire set, because this is 0, being of the order of dt to the power 3 by 2 at best. This is dt square, which is again higher than dt, and this contributes only one term, which is dw square, which is this dw square, and therefore, dw square is nothing but dt. Therefore, we have b square dt as the contributing term out of this, right. So, combining all this, what do we get? A, this is the first term, you got to now when you put dx equal to this expression, a into dg upon dx is the first term that we had there. This is the term that will go to the, that will be the stochastic term, b dg upon dx. This term will be as it is, and out of this term I will get 1 by 2 b square into this expression into dt. So, that is all that remains out of this, and that is precisely what is written here. dg is equal to a dg upon dx, that is from the first term. This is from the explicit t dependence, and this is from the dx square term, which contributes only one term, which is b square dt, b square dt. And this is the second term arising related to this the first term that we had in dx. dx is equal to a dt plus b dw. So, that is the term which contributes to this and this, and that is this is the final form of Ito's lemma. What is the now? So, we have dg is equal to this plus this. It is very obvious from this that the drift rate is given by this expression. Drift rate is what? It is a drift per unit time. So, that is given by this expression, and the variance rate is given by this. The square of this gives you the variance rate per unit time, because dw square will be equal to dt. So, the variance rate, that is the rate per unit time, the variance per unit time will be given by the square of this expression. This is a simpler form of Ito's lemma. In fact, it is a simplification of the Ito's lemma when our stochastic, you see we had looked at a stochastic process, dx is equal to a dt plus b dw. If I have a stochastic process where this is absent, in other words, my function is simply a function of time, explicit dependence on time, and Brownian motion dw and explicit dependence on time, then I can write through using a Taylor expansion in this form, and this expression again gives me dt this expression is already there with dt. So, I can collect these two terms together, and therefore, this constitutes the correction to the conventional calculus. This would have been there even if we talked about conventional calculus, and this term would also have been there even if conventional calculus was used. So, this is the piece that is additional when we talk about stochastic calculus. And if you have non-explicit time dependence, you can shift this term to the or rather you can shift this term to the right hand side. This will become 0 because you do not have any explicit time dependence. So, this becomes 0. This term will remain on the right hand side, on the left hand side, and this term comes on the left hand side with a minus sign. You integrate the expression, you get integral of f dash dwt. Now, without time dependence, without explicit time dependence, you get a integral of f dash wt dwt is equal to f wt. If the integration is between the limits t1 and t2, you get f w t1. On the integration of this, you get f w t1 minus f w t2 minus f w t1 by the integration of this, and you have this on the left hand side with the minus sign, and you integrate this with respect to t because the variable here is t. Now, let us use this to evaluate our example, our problem that we started with. What was our problem? Our problem was to work out d w square. This was what we wanted to work out. If I use f dash w t equal to w t, that means f w t is equal to w t square upon 2. Substitute my values here, I get integral of w t w t is equal to 1 by t w t 2 whole square minus w t 1 by 2 w t 1 whole square minus 1 by 2 integral f double dash w t will now be 1, because I am using f dash w t 1, f dash w t 1, I am using w t is equal to f is equal to w t. This is what I have assumed. So, f dash w t is equal to w t. So, f double dash w t is equal to 1. So, this becomes dt, dt integrated between t2 and t1 gives me t2 minus t1, and if you look at this carefully, this is nothing but t2, this is nothing but t1. So, 1 by 2 t2 minus t1 minus 1 by 2 t2 minus t1 is equal to 0, which is what we had arrived at earlier, that integral of w s dw s is equal to 0. That is what we had arrived at earlier, and that is what we are arriving at using Ito's lemma. The result is consistent with Ito's lemma. The result that we arrived at using summation by series is consistent with the result that we arrived through Ito's lemma. Right. So, we take a break and then we will talk about stock price distribution after the break. Thank you.